Good afternoon. This is from Dr.B.Vijayakumar. The another topic we discuss in this video is a domain theory of ferromagnetism. It also is in a magnetic material, the title. The brainstorming is what is ferromagnetic domain and what is ferromagnetic structures. This is all to be discussed from this topic. The introduction of ferromagnetic material and domains. The ferromagnetic material such as iron does not have magnetization unless they have been previously placed in an external magnetic field. But according to Curie's theory, the molecular magnet in the ferromagnetic material are said to be aligned in such a way that they exhibit in a magnetization even in the absence of external magnetic field. This is called as a spontaneous magnetization. It should have some internal magnetization due to quantum exchange energy. So according to Curie's hypothesis, a single crystal of ferromagnetic material is divided into large number of small regions called domain. This domain have spontaneous magnetization. So each domain is formed in one dipole. But the direction of the spontaneous magnetization vary from domain to domain and are oriented in such a way that the net magnetization of the specimen is zero. So this diagram is a form of based on the field applied field wise. First one is an external field is absence, then weak applied field and a strong applied field. So the magnetic field is applied. The magnetization occurred in the specimen in two ways. One is moment of the domain wall, then another one is rotation of the domain wall. The moment of the domain wall take place in a weak magnetic field. Due to this weak magnetic applied in the specimen, the magnetic moment increase and hence the boundaries of domain are displaced. So that the volume of the domain change in the figure, it will be shown that by the rotation of the domain wall. This is the second property. The rotation of the domain wall take place in a strong magnetic field. When the external field is high, then the magnetization change by means of rotation of the direction of magnetization towards the direction of the applied field. It also shown in the figure. The domain theory of ferromagnetism is based on the four types of energy. The one is exchange energy, anisotropic energy, domain wall energy, and magnetostrictive energies. These four energy become involved in the each domain and in each magnetic material of ferro. The first one, exchange energy or magnetic field energy, are the interaction between the energy of adjacent dipole to align themselves. It's known as exchange energy or magnetic field energy. The exchange energy has established a single domain in a specimen of ferromagnetic and it's shown in figure. The development of free pole at the domain, an external field will be produced around it and the configuration will have a high value of magnetic field energy. In other words, it's an energy required to assemble the atomic magnets into a single domain, and this work done in this stored by potential energy. The magnetic energy can be reduced by individual the specimen into two domain. It also shown in that figure. This is all the figure to the form of how the domain it will be rotated and change of the direction to based on the applied field wise. Then second is an anisotropic energy. It becomes conversion of easy direction to hard direction. The easy direction of magnetization, weak field can be applied, and the hard direction of magnetization, strong field can be applied. The producing the same saturation magnetization along both the hard and easy direction. Strong field are required in the hard direction, then the easy direction. So this graphical representation is clearly executed in the easy direction and hard direction of the magnetic material dipole moment to based on that the energy conversion. So the easy direction we consider in 1 0 0 and medium is in a 1 1 0 and hard direction is 1 1 1. So this is to be identified of based on the material wise. So this data will be given from in iron. Then domain wall energy or Bloch wall energy. Bloch wall is in a transition layer which separates the adjacent domain magnetized in a different direction. The energy of domain wall is due to the both exchange energy and anisotropic energy. The two types of Bloch wall it become arise to the based on the spin alignment of domain. The one is in a thick wall and another one is in a thin wall. The thick wall, the spin at the boundary are misaligned, and if the direction of the spin change gradually, it lead to a thick Bloch wall. Here the misalignment of the spin are associated with an exchange energy, that is a potential energy. So the wide wall and thin wall, based on the exchange energy, become change of the direction of the dipole moment in one direction to another direction. The last one energy is in a magnetostrictive energy. When the domain are magnetized in different direction, they will either expand or shrink. That means change in dimension. That is a very important word to be discussed in magnetostriction energy. So the material change in dimension when it is magnetized. So this phenomena it's called as a magnetostriction, and the energy produced in this striction, that is called as a magnetostriction energy. So the deformation is different along different crystal direction, and the change in dimension depend upon the nature of the material. Example, nickel. So the nickel, its change in length, it decreased form of the applied field. These are the reference I prepared from this PPT of the domain theory of ferromagnetism. Thank you very much. We discussed in another one video in another one topics. Thank you.